This list is available at the start of all of my videos. When you look at my lessons online, the slides are sometimes blue, meaning those are not testable items. And if the slide has a yellow star, then that's clearly what it is you need to know. Distance versus displacement. Your car has an odometer that records distance. It just accumulates the terrain running under the wheel, even if you drive in circles or drive backwards. You cannot get that number to go down. So it's recording the total distance the vehicle has traveled. A GPS, on the other hand, can report displacement. It records your exact change in position, so it should go back to 0 when you get home again. Odometers are blind to position. The GPS is not. If you left home and drove to Toronto, then returned home at the end of the day, which of these devices would record 0 kilometers at the end? Here's an interesting one. Why is it illegal to tamper with the odometer and make it record a lesser number? This is a practice called rolling back. If you read the links in the lesson that goes with this video, you'll see some hefty fines of almost $300,000 to $400,000 for people that were caught rolling back odometers. Scalar numbers are numbers with units, of course, like 10 meters, but they only have magnitude. That means a number without reference to direction. If I say to you v equals 20 kilometers an hour, which is speed reported as a scalar because there's no direction. Mass equals 20 kilograms and temperature equals 37 degrees Celsius are inherently scalars. You can't have 25 kilograms northwest. Vectors have direction and magnitude. From the word carry away, a disease vector points to the creature spreading a disease, as in the mosquito is the malaria vector. In math and science, it means the direction that is carrying you away. Distance equals 20 kilometers north, or d equals 20 kilometers n, is a vector distance whose magnitude is 20 kilometers. Velocity equals 120 kilometers an hour south is a vector velocity whose magnitude is 120 kilometers an hour. Because vector versions of speed and distance are used a lot, they get their own name. If I ask you for velocity, then it means I want direction. If we say displacement, we want to know where you are now. Where are you out of place? We need a direction. In summary, displacement is simply distance with a direction added. Velocity is simply speed with direction added. If we don't want the direction, we can ask for the magnitude of the vector. This is shown with absolute value bars used in math. So it looks kind of scary, but distance is equal to the absolute value of displacement. Speed is the absolute value or magnitude of velocity. Let's look at how we report our position. The difference between polar and Cartesian coordinates. You actually already know this. I'm just giving it a name. Let's say I have a map set up with northings on one side, eastings on another. You might say, why not north and east? Military grids, they like to call it northing and easting for some strange reason. And we have a person who goes on this rather bizarre walk over an interval of time. Let's count how many steps they took. This person took a walk over time. How far did they actually travel? Well, I'm going to do a little bit of a cheat here and start running out little increments. That's 1 kilometer, 2 kilometer, 3, 4 kilometers, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 kilometers in path length. Okay, so they walked 16 kilometers. Now, where are they from their starting point? Well, they walked from the start to their final position. You can see They moved this many steps east, that many steps north to this final position. 7 kilometers east, 8 kilometers north. That's their displacement vector, the line connecting their start to where they are now. So what is the length and direction of their displacement vector? Well, heck, this is just like grade 9, even grade 8 math. If I give you a triangle whose sides are 7 and 8, how do you calculate the hypotenuse? Do you know any way of calculating D? Now you could take a stab at it here and go, this side is going to be longer than the other two sides, so maybe it's like 10-ish, something like that. Well, let's take a look at what we can do. How many of you know Pythagoras' theorem? You're going to square 7, square 8, add them up, and take the square root. 10.6, I said, look kind of like 10-ish. Now we need this angle. Let's think about this. If you have a triangle of 7 and 7, that angle is 45 degrees. So this angle is going to be a little bit more than 45. But we can use trig if you wish. It is not required in grade 11. It's required in grade 12. But heck, you're home right now. Why not make sure you're ready for grade 12? So how do we get the angle? Well, tangent is opposite over adjacent, and we already have those two numbers. So if I took my calculator and I plug in 8 over 7, then hit the inverse function, it tells me 48.8 degrees. So that is our bearing or direction of our vector. Put it all together and our displacement vector is 11 east, 49 degrees north. Now why didn't I just write 49 degrees? In math class that would be enough. But for real world vectors they tend to say face east, then turn 49 degrees north. Right? That's all there is to it. Now, we haven't done any physics yet because I skipped something between the previous slide and this side that makes this answer not complete. And a real picky teacher would cost you a mark. There's something missing on this page. Something I dropped here, here, and here. Did you see what I forgot to include? That. Got to make sure we have those units as well. So yeah, it goes, you go like, I can handle the number 11, but you'll get used to it. And if it confuses you, I'll use different colors. That's what I like to do a lot. There we go. See? Isn't that prettier now? This vector is all dressed up for dinner. He's got a number, he's got units, and he's got a direction. This is a man with the plan. And a harpoon. That's what we call that little vector arrow when it doesn't have the other side. It's called a harpoon. This is called the magnitude of the vector. These are the units of the vector. And that's the vector's direction. Let's go back to the terms polar and Cartesian and see if we can make sense out of them. Cartesian coordinates give you the x and y. So in math class, a teacher might say, plot 7, 8, and they've given you an x and a y direction. On a map, that would be east and north. But polar coordinates tell it to you different. They tell you a direction and a range or a distance, very much like a radar screen. Trig connects these two methods. The person who goes like, it's not legal to crosswalk like that, so I'm going to march this way, and then I'm going to turn and march north. And somebody says, why don't you just go in a straight line? Because that's not following the rules of the road. But if you're a bird or a plane, why on earth would you go this way? You simply go straight for the target. And the term R for range is used frequently. The military would say, what's the range and bearing of the target? Or if you want to get really fancy, they can say range and azimuth. Who cares? You've actually been using both coordinate systems, they weren't given a name. Slide is blue, you're not going to be tested on it. What happens when we want to add these guys up? In ordinary math, you would write c squared equals a squared plus b squared to get this triangle. But if you put vector notation on it, you can just write it like this. Vector d is the addition of these two. In other words, to go from here to there, you can do it in two separate passes. This actually implies Pythagorasses theorem. Okay? Am I going to ask you about polar coordinates? No. You'll get to it in math class, but I'm just showing you there's two different ways of getting to a destination. X and Y coordinates, or I give you a direction and tell you how far to go. This is what it looks like in practice. When they started firing cannons really big distances, after about the 1880s, you really have to plot your trig in order to get it going. And back then, without computers, they had these large mechanical computers that they could use to aim the firing solutions for their guns. By the end of World War II, they were actually getting mechanical computers. So as this guy dials in what the target's supposed to go for, it will give him the exact range, bearing, and actual elevation of the cannon to hit the reported target. This part of the ship is deep inside. It's the brain works. This part of the ship get destroyed, the ship is done for. They won't be able to shoot at all and hit their targets. This, of course, is your classic old display, the polar coordinates on an airport. And again, early computers in here helping to coordinate. And the radar screens are also in polar coordinates. In World War II and other wars, this is what they might have on the battlefield. This is actually a primitive calculator, and you aim where you want the gun to fire. You slide different arms out to the distance, and it tells you the settings for the cannon to hit the target. By the 1960s, this is what you got when you wanted to aim a cannon. So there's an awful lot of vector mathematics going into firing a cannon. Today, you can go to an artillery page website and I'd like to order an MK3 artillery computer system. And now you just type in what you want to destroy and it tells you where to point the gun. Kind of scary. By the 1880s, aiming of projectiles, the vector mathematics required to hit ships, particularly when they were starting to disappear over the horizon, got really complicated. And their aiming systems involved these gigantic things like this to get the vector bearing of the enemy ship. And since they had to get a clear sight and focus on it, there was a brief time period where this is what camouflage looked like near the start of World War I, called dazzle pattern. Made it very hard for these guys to focus on the ship, make sure they got it nailed, and gave the range for the artillery guys to plot their vector firing solution. And this is why many of these ships had these giant towers. They had range-finding guys all over the ship in many locations trying to get the exact distance to a target. And you can imagine how freaking naked you'd feel up here. Here's the rangefinder sticking out on this side of the ship, and there'll be the other end of it there. It's basically giving you really widespread eyes to get the bang-on range. So there's a lot going into firing a cannon, and an awful lot of it is vector physics. There's a huge range. And man, oh man, I'd hate to, the only time I'd want to be this guy up here is if the ship is sinking. You might get to the last minute, or maybe the ocean's shallow enough you're still sticking out, but that's a horrible place to have to be during battle. And you can be sure any enemy planes would want to blow this rangefinder out of the water. Without the rangefinder, these guns are useless. And here's a smaller version. And here's another one here. He's not sleeping. He's actually getting the range to an enemy target. And believe it or not, they still use those rangefinders. It's not always computerized now. Well, what does this vector distance have to do with history? Well, in 1905, the Russians got into a battle with the Japanese. And the Russian fleet had to leave the Mediterranean and go all the way around planet Earth, basically, to defend their territory out here because they had no overland route. And everybody thought at the time, well, the Japanese were a subhuman race. The Russians were one of the biggest, European nations. They'd clean the Japanese clock. And instead, the Russians got slaughtered. 30,000 kilometer voyage, largest fleet ever, including today, sent into battle. The world waited a whole year while the Russians steamed, sure to destroy the Japanese, and the Japanese wiped out 2 out of 3 Russian fleets. There's the Russian guy, there's the Japanese guy. Still fighting like the days of soldiers on horseback. And what did them in? The Japanese had moved to these better rangefinders. The Russians were still using an older system. These rangefinders use 2 eyes and give you great stereo depth. The Russians were using this old style, where you basically tried to guess the distance by the height of the ship. And this actually requires you to know what ship you're shooting at. You have to know its height above the water. So if you want to know how far this target is here, you count the little blips that it's crossing. Very poor rangefinders. So the Russians got completely destroyed on basic vectors. They hit nothing when they fired at the Japanese. In terms of history, 1905 is only 10 years before World War I and like 15 years before the Tsar was killed. This battle destroyed the remaining confidence the public had in the Tsar. And it was part of his many catastrophes. The man was cursed. Every move he made was wrong. This war with Japan just completely drained Russia out of 2 of its 3 fleets, and there was a full-on military mutiny afterwards. And then he wades into World War I. It's just, the guy was a walking catastrophe. Anyway, that's my little aside. Let's go back to vectors. Let's change it from the topic of war to a puppy! I want you to determine how far away the puppy is from home by just examining this. You can count the lines, and you can just give me the vector bearing because I put a protractor behind. And so that's your first assignment, telling me the distance and the displacement of the puppy.